Okay, so welcome back in the method of Stodlas. So we were studying about this table, like how to fill this table. So first row that we have written is assumed deflection. So that assumed deflection I have taken 1, 1 and 1. Deflection of these three masses. You can assume any value, but the number of iterations that you have to do will be more if you cannot assume, or if you are unable to assume an appropriate value. So your number of iterations will keep on increasing. So I request you to just think on this system and then assume a suitable value so that number of iterations will be less. Then second row that we have taken here is inertia force. So we know formula for inertia force is m omega square x. So over x is this one, 1, 1 and 1. And m will be as in every quantity. So I am taking m outside as common. Then I have written omega square and omega square. Then third row is spring force. So spring force, as I have mentioned, will keep on increasing from right hand side to left hand side, and that will be the sum of inertia forces. So see here, this inertia force I will write here. Then here I will write this one plus this one. So 2 omega square. Then here this one plus this one, that is 2 omega square plus 1 omega square, that is 3 omega square. And m is outside as common. After that, next row is for spring deflection. So for deflection, we know that deflection is F by K. So this is our force F, like m 3 omega square. And this is m into 2 omega square, and this is m into omega square. So I will divide this one by K. So m by K I will keep outside, and this one is 3 omega square, 2 omega square and omega square. Then next row is calculated deflection. That is, as I have mentioned, that deflection will keep on increasing from left hand side to right hand side. So this is common m by K. Then deflection here of this mass m1 is 3 omega square, I have written here. Then deflection of this mass is 3 omega square plus 2 omega square, that is 5 omega square. Then deflection of this mass is 5 omega square plus omega square, that is 6 omega square. Then I will take a ratio. So I will divide this 3 omega square by 3 omega square, and every quantity by 3 omega square. So this is 1, and this one is 5 omega square divided by 3 omega square. So 5 by 3, that is 1.67, and this is 6 by 3, that is 2. So this is the deflection of these masses that you have assumed here, that is 1, 1 and 1. And what we have got the result as 1, 1.67 and 2. But this is not the final answer. Our final answer will be the ratio when this assumed deflection will be equal to this one. The answer will be equal to the answer, then this will be the final answer. So as we can see, our assumed is something different and answer is something different. So we will assume this quantity again as our assumed deflection. Then we will calculate all these 5 rows. We will fill all these 5 rows again. So you can see these here. I have calculated. See here. So our assumed deflection is 1, 1.67 and 2. These answers only, these ratios only I have assumed here. Then inertia force. So 2 into omega square, m is outside, 1.67 omega square and omega square. Then spring force, that will be 4 points. Spring force will be keep on added from right hand side to left hand side. So right hand side means this one. So 2 omega square, then 2 plus 1.67. So 3.67, then 3.67 plus 1, that is 4.67. Then spring deflection. So spring deflection will be F divided by K. So F means this one. So I will divide this one by K. So m by K I will keep outside, and I will mention these same quantities again. Then calculated deflection. So calculated deflection is, as I have mentioned, deflection will keep on increasing from left hand side to right hand side, right? So this is 4.67 omega square, and this will be 4.67 plus 3.67. So this is 8.34. And this is 8.34 plus 2, so 10.34. Then I will divide all these three values by 4.67 omega square. So 1, 1.79 and 2.21 I am getting. So now you can see here what we have assumed is 1, 1.67 and 2. And what we have got as answer is 1, 1.79 and 2.21. So we can say that this is not converging. So still we have to do exercise again. So this is the third table that I have filled here. So this is the third table that we have, this one. So here our assumed deflection is, that is 1 and this is 1.79 and this is 2.21. Okay, and this is inertia force. So this is our assumed deflection. Then inertia force will be m omega square into x. So m omega square into 1, m omega square into 1.79, m, that is outside, omega square into 2.21. Now our spring force, that is 2.21, then sum of these two here, then sum of these two here. Then spring deflection, that is simply F by K. So I will keep outside m by K and I will write this again. Then calculated deflection. So calculated deflection will be keep on added from left hand side to right hand side. So 5 omega square, 5 plus 4, 9 omega square, 9 plus 2.21. So that is 11.21 omega square. And then I will divide these all three values by 5 omega square. So I have got the answer like this. That is 1, 1.8, 2.24. So what we have assumed is 1, 1.79, 2.21 and we have got the answer 1, 1.8 and 2.24. So still we can say that although these vectors are very close enough to each other, but we can go for one more iteration because it not yet converges, right? So let's take the final table that we have calculated here. So in this table, by repeating the same procedure, what we have got 1, 1.8 and 2.24. So exactly same as what we have assumed. So now we converge to final result. So this is our vector or mode shape, that is a value of x1, x2 and x3, that is 1, 1.8 and 2.24. So this mode shape I have written with 5. Now we have to find out what is our frequency, fundamental frequency. We got the vector, that is 1, 1.8 and 2.24, and now we have to calculate the frequency. So see here how we have calculated the frequency. Sum of these vectors equal to sum of these quantities. So omega square I have taken outside common, this omega square and omega square into m by k and to sum of this. So from here we have got omega 1 equal to 0.446. As you can see, there is no crossing, all values are positive. So there is zero crossing, means this vector is corresponding to the fundamental frequency or first frequency. So this is our first frequency omega 1 or fundamental frequency. So this is how we can calculate the fundamental frequency and corresponding mode shape by using Stodla's method. Now let us conclude this method by seeing some important points about this method. So see here, these are some points. Method is capable of computing only fundamental frequency and corresponding mode shape. Modal response analysis of the weighted first frequency generally gives, that is 70 to 80% of the first mode. Iterative scheme, so you can easily program this one in MATLAB or any other computational softwares. You can program this one. Can be applied to either discrete or continuous systems. Basic concept is deflection. So as you know, he has taken deflection as the basic concept. So we have assumed deflection initially and then we will proceed further. So fundamental frequency for free vibration analysis. So there was no external force. And this is to cause the deflection, as there was no external force. So to cause the deflection, we have used inertia force as the force. And this method is very effective and popular for inertia dominated systems. So this was all about Stodla's method. I hope this video will help you to understand the depth of the Stodla's method. Thanks for your patience. Thank you so much.